Yeah. Uh-huh. Perfect. Okay, so we can get started. So last lecture starts this 4-lecture sequence of estimation and hypothesis testing. So last lecture is estimation 1. And we're really talking about, we were talking about estimation population mean. So it's a continuous population. And then we are interested to do inference on the mean. So what do you do is you obtain a sample from the population of interest, and then you use the sample mean to represent or to estimate the population mean. And why do we want to use sample mean? Because there are several very nice properties of sample mean. The first nice property of sample mean is it's unbiased, which means expectation of the sample mean, it's always the population mean. So that is the first nice property. The second nice property is its variance, which is the population variance over n. Our standard error is the standard deviation of the population over square root of n. This variance is the smallest variance estimator among all the estimators. What? Microphone? Is it better? Is it better? I don't think this one is working. This one? No, none of those working, right? Oh, okay. Can you hear me? Okay, so I'm just trying to speak louder. So it's the minimum variance estimator among all the unbiased estimators. So that is a second nice property of the sample mean. So we talked about these two properties, and remember, these two properties are independent or irrespective of the sample size. No matter what sample size you have, the sample mean is always unbiased and always have that variance form. And then we talk about if you have a sufficient large enough sample, which means the sample mean is estimated over a sufficient large enough samples. So if that is the case, the sample mean has a third very nice property, which is given by the central limit theorem, which basically means no matter what is the underlying distribution of that variable in the population, the sample mean is always approximately normal distributed. And this approximation can take place if you have sufficient large enough n. So remember, there are 3 properties. The first two, the unbiasedness and the variance, does not depend on sample size. And the third one, when sample size is large enough, the third one kicks in, and that is the central limit theorem, and that refers to the distribution of the sample mean. Okay, so we talked about those 3 properties. And today we are going to continue the last lecture where we haven't finished. And that is when you talk about estimation, there are 2 points. One is a point estimate and the other one is an interval estimate. Interval estimate is really give you a confidence interval or give you an interval that quantifies the confidence that you have in associated with your point estimate. So if x1 to xn denote any independent random samples from the same population with mean, mu, and variance sigma square, our goal is to estimate the population mean, which is mu. So we have already known that x bar, the sample mean, is a good point estimate. However, we want to have a confidence interval that x bar minus and plus a, such that there is 95% of chance that the population mean lies in this interval, x bar minus or plus a. So this is a definition of an interval estimate. So mu is within, remember mu is a population parameter. Population parameter is within this interval with 95% of chance. So this is the definition of an interval estimate. And we talk about the properties of x bar, and now we move on to interval estimate. Remember, when you talk about interval estimate, we actually have to use the third property, which is central limit theorem. So when you talk about the interval, when you have a probability of 95% or 90% that within this interval, you are actually implicitly assuming that it's large enough sample size. Because given large enough sample size, x bar, you have a normal distribution associated with x bar. So with that normal distribution in place, you can work out this property. So basically, when you talk about an interval estimation, you are implicitly using the central limit theorem, and you are implicitly assuming that the x bar is achieved among a large enough sample size. So from central limit theorem, remember x bar is a normal distribution, and the mean of x bar is mu, and standard error of x bar is sigma over square root of n. So we talk about transformation, or we talk about standardization. So given the mu and the standard error, we can get that x bar subtract this mu over standard error should be, this is a standardization. So the result from that should be z, which is a standard normal distribution, right? So this part is from central limit theorem. However, given this one, this is not enough to estimate the interval estimate, because sigma right here, we do not know. This is a population parameter, remember, and we do not have a prior known sigma in place. So what should we do? A very natural replacement or very natural substitute for sigma is the sample standard deviation. So sigma replaced by s. So we have this formula, and the only difference now from here to here is x bar subtract mu over s over square root of n. So we made this replacement of sigma by s, the population standard deviation by the sample standard deviation. And after this replacement, we know that without this replacement, it is a normal distribution, standard normal distribution. With this replacement, is it still a standard normal distribution? The answer is no. With this replacement, the distribution is no longer standard normal. The distribution is called t distribution, or sometimes you can put the full name, it's called student t distribution. So what is student t distribution? Student t distribution is a very similar distribution to normal distribution. However, it has heavier tail than normal distribution. And for t distribution, it has one parameter, and that parameter is called degrees of freedom. So when you talk about t distribution, you always are talking about t distribution with what degrees of freedom. So here, x bar minus mu with this replacement of s over square root of n, this one is no longer standard normal distribution. It is a t distribution with n-1 degrees freedom. So remember, the degrees freedom is the sample size minus 1. And as we talked about, S is in this formula. So this page gives you a little bit introduction about t-table that you can see very frequently in a statistical textbook. So t-table is very similar to a normal table, to a normal standard normal distribution table. The only difference is, so you have the percentage points of t distribution, and then the difference is you have a row which is characterized by the degrees of freedom parameter. So you have degrees of freedom 1 to some number. And then, so here it gives you percentage. So if it's 0.75 percentage, this one is 1. So here it basically gives you that a 0.75 quantile or percentile of the t distribution is 1. So this curve compares the t distribution with normal distribution. And we have right here the solid curve, solid blind curve. A black curve is the normal distributions, standard normal, normal 0, 1. And then we have the dashed line, which is very similar but with a little bit of heavier tail. That is a t distribution with 5 degrees of freedom. So you can see that t distribution and normal distribution, they are very similar in terms of their shape. They are also symmetric. It's also symmetric around 0. It's also a bio curve. The difference is it has heavier tail. And then here in this plot, we examine different t distribution with different degrees freedom. So again, the solid line is normal distribution. And then this is a degrees t distribution with 2 degrees freedom, this long dash curve. And then this short dash curve is t distribution with 9 degrees freedom. So you can see the trend is with the increasing number of degrees of freedom, this t distribution curve approximately looks more and more similar to a normal distribution. What is the benefit of using one?
Like if you have data, how do you know if you should analyze it with a t-test or standard normal distribution?
We haven't talked about test at all. So is that your question? So this is really about estimation. So I think your question really refers to different testing or hypothesis testing that the reference distribution. We will discuss more in the next couple of lectures. For this one, when you talk about, when you are inferring about the population mean, and if you know the population parameter, which is sigma right here, if someone tells you exactly what is the sigma, you can use standard normal distribution to estimate the confidence interval. Here we're only talking about confidence interval. We're not talking about testing at all. And then most of the chance, or 99% of the chance, you can't know the sigma because it's a population parameter. So you use S to replace here. So with this replacement, once you use S to replace, you are no longer referring to a standard normal distribution. You are using a t-distribution. However, what you are using a t-distribution still to get a confidence interval or to get an interval estimate. We haven't got to any testing yet. So, your question of which test to choose, whether it's t-test or normal test, we haven't got there yet. Okay, so the normal density and t-density, essentially, if the degrees freedom is small of a t-distribution, it is more different from a normal distribution with heavier tail. If the degrees freedom is large enough, it is essentially identical to a normal distribution. So here we give you a little bit comparison of the 97.5 percentile of t-distribution and normal distribution. So you can see that, remember, the bigger the degrees freedom, the closer the t-distribution to the standard normal distribution. So you can see this is z 0.975, which is 1.96. This is fixed because this is from the black solid curve. It's fixed. And then with different degrees freedom of t, you can see that this value range from 2.7 to 2.26 to 2.0. So you can see with the degrees freedom increase, this quantile approximately approach this quantile from the normal distribution. And then if degrees freedom equals 60, it is 2, which is very close to 1.96. And then if you have infinity degrees freedom, it's actually 1.96. Yes? Yes. And this is, if you want to intuitively understand those numbers, remember t-distribution has a heavier tail. So it has heavier density on the tail. So that means for the same 0.25 alpha area, if it's a heavier tail, you would need a bigger quantile here to achieve the same alpha. Does that make sense? So that is why when the degrees freedom is small, for the same alpha, the quantile is bigger for the t-distribution. Let me try to draw this curve to make it easier. So remember, this is standard normal distribution. And then we are interested in if this part is 2.5 quantile. So this is your alpha. So this one is 1.96, right? This is what we talk about standard normal distribution. Suppose now you have a t-distribution. And t-distribution, the difference is it's heavier tail. So it's like this. So this one is a t. So remember, t-distribution has heavier tail, which means the area in the tail is more likely. So that's okay. If that is the case, if you want to achieve the same alpha level, you do not need to be this close. You can be a little bit further in this line to achieve the similar alpha, right? So for the same alpha, this quantile, let's say this is this freedom of 4. This quantile is intuitively, it should be bigger than 1.96 because the density is more heavy on the tail. So 1, 2 point. So if it's 4 degrees freedom, this quantile is almost like 1 unit bigger than 1.96. You just need to push it even further. So this is the intuition behind why the degrees freedom decide different quantile value. And then if degrees freedom gets bigger and bigger, this quantile, so basically these two curves converge to each other. So these two quantile converge to each other. So this, when degrees freedom gets bigger, this quantile gets to 1.96. Yes?
Because I'm very slow. So the degrees of freedom then is the number of samples that you've taken to generate your sample mean. Is that correct?
Yes. So so this n here is the number of samples that you estimate the mean from.
So
And the degrees freedom is n minus 1.
So if you chose, say, 3 samples to get a mean, your degrees of freedom would be 2.
Yes.
And then you'd have this long tail, which makes sense because
Yes.
your expectation that you're getting the real mean accurately is not so high.
Exactly. Yeah. Although your sample that when degrees freedom is only 2, even t degrees freedom of 2 is not a good approximation, because at that moment central limit theorem is really not safe. But essentially you're correct. Okay. So this curve gives you from a t-distribution, which is very similar to a standard normal distribution. If you have this 2 quantile, which is alpha over 2 and 1 minus alpha over 2, if you have this 2 quantile, this area is alpha over 2 and this area is alpha over 2, so the middle area is 1 minus alpha, right? So this is in a t-distribution. And how do we use a t-distribution to get the confidence interval? So this is what we do. For t-distribution, it has probability 95% of the chance that a t-distribution is within this 2 interval, right? So remember, this t is x minus mu over s over square root of n, right? So let's see. So what should we do here? Let me write here. So from this curve, we have that the probability of a t-distribution, of a variable with t-distribution that within this 2 interval, within this 2 critical value is 95% of the chance, right? And then we also know that x subtract mu over s over square root of n follows a t-distribution with this n minus 1 degrees freedom, right? So no cycle here. So from here to here, I simply just replace the fact that x minus mu over the standard error is follow a t-distribution, right? So if this is the case, what I should do is I just do some algebra to isolate this mu here. Right? So you can work out that x subtract t n minus 1 alpha over 2 times the standard error right here. So from here to here, it's basically doing the algebra that isolates this mu from this form. So basically, you need to get x right here, and then you need to multiply by this denominator right here, and you need to do that for both sides. So essentially, you get to this probability that mu, which is a population parameter, lies within this two boundary or two interval, have 95% of the chance. So that means it turned out that those two boundary, they have, this one is a negative part of this one. That is because this one and this contour is symmetric around 0. So that means you can simplify this by that by a plus minus sign here. Essentially, it is symmetric around x bar right here. X bar actually. It's symmetric around x bar. So this interval is called the 95% confidence interval estimate for the population parameter mu. So remember that the point estimate for mu is x bar, and then in addition to a point estimate, we also have a confidence interval estimate that associated with this x bar, and this confidence interval is centered around x bar. So it's x bar plus something minus something, and that quantifies this boundary or quantifies this interval. So essentially, it's right here. This page is what I wrote there. So mu is bounded by the lower bound and the upper bound by 1 minus alpha chance. So I actually write here is also kind of generic. So here you can actually write by 1 minus alpha. And alpha here, if it's 95%, alpha here should be 0.25. So this is the confidence interval. The confidence interval for the mean of normal distribution or for mean of a continuous variable is x bar subtract this one and x bar plus this one. And then the confidence interval for large samples is also the same case. It's the only difference here is when n is large enough, you can actually, this t distribution, this t quantile, can be also replaced by this z quantile. And that is what we saw in the previous table, that if n is large enough, this t quantile is approximately this normal quantile. So the formula, in this formula, that if you have this quantile, if n is very large, it's large enough, you can actually use z quantile to approximate that. And then the short notation is x bar plus minus the z quantile of s over square root of n, and that is because you have large enough sample size. And also from this formula, you can see that what is the length of a confidence interval? The length of a confidence interval is around x bar, and it's plus and minus this distance. So the overall length is 2 times of this distance. It's 2 times t quantile times s over square root of n. So that means a confidence interval, the length of a confidence interval is decided by 3 parameters or 3 facts. The first one is sample size. If sample size increase, so that is the square root of n here. So this one, if n gets bigger, this ratio gets smaller. So that means the length gets smaller. And then if s increase, so remember this s is the variability of the distribution of individual observation, which is s is the standard deviation of sample, your sample. So basically, no, it's not standard deviation. S is the estimate of population variance or population standard deviation. So if this s gets bigger, this confidence interval also gets bigger. And then the last thing that determines the length of a confidence interval is alpha. If alpha decrease, the length increase. So those are 3 factors that decide the length of a confidence interval. Remember, it's really about this formula. If n gets bigger, then this whole thing gets smaller, and then this confidence interval gets smaller, right? The length gets decreased. And then if s gets smaller, which means if s gets, the population variance is smaller to start from, and then this whole thing will get smaller and the length would get smaller. And the next thing is alpha. If you're interested in a bigger alpha, which means you are only interested in a shorter coverage, so this interval will be smaller, and then this length will be smaller, right? Yes?
Is the n minus 1 comma 1 minus alpha over 2 all just pertaining to that t value? Okay,
Yes.
so it's whatever that t value is times s divided by n square root of
Yes,
n.
yes, yes. So for example, if we want to get suppose, let's see. Suppose n equals 29, and then what is, you got x bar and you got s. So then the confidence interval of mu, the population parameter, equals, so this t, n minus 1 is 29, n is 30. So this t, 29, 1 minus 2.5 over 2, this value should equal to, refers to your table right here, 2.045. So and suppose you have S here. Let's make it some number. So this suppose is 2, and let's see X bar is 5. This is your estimate that you achieve from 30 samples. Okay, so that means, how do you write this confidence interval? The upper bound is X bar plus this value 2.045 multiplied by S over square root of 30. So S is 2. And then the lower bound is 5 X bar minus 2.045 over 2 over square root of 30. And thus give you 95% interval. So if you continue to calculate this should be 5 over 4 over square root of 30, and then this is 5 subtract 4 over square root of 30. And this is the confidence interval formula. So this whole expression refers to this one value, which is a quantile value. So that actually concludes the lecture on estimation 1, population mean. So remember, the lecture 1 of estimation is actually very straightforward. It's really talking about when you have a population and you are interested in the population mean. What is your estimate? How do you estimate population mean? So the point estimate for population mean is sample mean, and the confidence interval or the interval estimate is by this formula, which actually utilizes the t-distribution. And t-distribution essentially relies on central limit theorem, which assumes that X bar is estimated over a large enough n. Okay? Do you have any questions with this lecture? Sure.
Let's say your samples and you're actually gathering sample mean values. So, let's say you're pooling samples, you're pulling enough tissue in order to get enough samples, and then you take the average. So each of those ends are actually means. You have to go through. Do you just use, instead of doing the standard error of the mean, to actually just get the standard deviation?
I think here you are essentially means that each of the sample, each of the population, each of the unit in your population is actually a mean.
Yeah.
So that has no difference from what we talked about in that lecture, because we're talking about a general population. The only unique feature of your population is each of the unit is actually a mean representative. So if each unit is obtained from large enough sample, so that basically essentially means central limit theorem kick in, that your underlying population is actually already approximately normal enough.
So in that case, your n, even though it's pooled, it has to come from the population that's greater than 30 or something like that.
Exactly. Yeah. But what we talked, it still applies. It's still standard error, and it's still, like how do you estimate the interval in those? Yes. Okay. So this lecture, actually the formal content of this lecture is the second part of estimation. So what is the difference between the second part and the first part of the estimation? because second part we are going to talk about a special case of estimating a population parameter, and this population parameter is population proportion, or sometimes you call population prevalence, or sometimes you call population probability. So that's a different terms to reflect this, but essentially it is a population proportion or population preference. So the setup for this one is, suppose you have this population is represent the number of success in an independent trial. So suppose you are looking for, I think I have an example right here. Okay, suppose you want to estimate the prevalence of melanoma in this age interval of women in US. So essentially, you want to estimate the prevalence of a disease or prevalence of a certain event. And then suppose you get 5,000 samples as your sample. And you found 28 of those have this disease. So your population in this example is all the women that within this age interval in US. So that is your population. And your task is to estimate the prevalence of this population to get melanoma. And what do? A researcher go ahead and obtain a sample 5,000. And she count in each of these 5,000 women whether or not a particular sample has melanoma. And then in the end, she got 28 of those has melanoma. So this is the situation. And your task is to use those numbers, 5,000 and 28, to estimate in the general population what is the prevalence of melanoma. And because you have learned lecture 1, you know that if you're given this task, you not only need to provide a point estimate, you also need to provide a confidence interval that is associated with your point estimate. So, how should we tackle this problem? Suppose we give it some notation. The prevalence of this disease, the population proportion, is in this age group is P. Suppose we denote that by P. So mathematically, now your question is, how do you estimate P? Right? So parameter P is unknown population proportion of success or of an event. And then you have a sample. And in your sample, you can estimate the sample proportion of event, which is P hat. So P hat can be estimated from X over N, which is the number of success over the total number of experiments that you have. So in this example, the number of success is 28, or the number of events is 28, and the number of experiments, that's the total number of your sample, which is 5,000. So it's 28 over 5,000. And so here, implicitly, I'm using X to denote the number of events over N independent trials, right? And because we have learned binomial distribution, you should know that X should be a binomial distributed random variable with N and P. N refers to 5,000 because X is the number of success over 5,000 trials or over 5,000 samples. So N is 5,000 here. What is P? P actually is the parameter of interest, which is a population proportion of success. So P is eventually your task to estimate. Remember, this P is not your sample proportion. It's the population proportion. And you estimate P from your sample. So this is some facts that we have learned. X is the number of women with disease among the small n women samples that you have in total. And then X is a binomial distribution with n and p. Recall that when we learned in the previous lecture, expectation of X is n multiplied by p, so n times p, and variance of X is n times p times q. And q is 1 minus p. So those are what we have learned. So, like what we did for the sample mean, there are several things that we want to study in terms of statistic or in terms of estimate. The first thing that we want to study is whether or not it is unbiased, right? Unbiasedness, that's the first property that we want to examine. The second property, what is its variance? What is the variance of the sample proportion estimate? Or what is the variance of p hat? So what is the mean of p hat? That's the first thing. What is the variance of p hat? That is the second thing. What is the third thing? The third thing is what is the distribution of p hat? So let's go that in that sequence. P hat, remember, is x over n. That is your sample proportion. That is your sample estimate of the proportion. And expectation of p hat is expectation of x over n. N is a constant. N is not a random variable. So n can be taken out of the expectation. So it's essentially expectation of p hat equals expectation of x over n. What is expectation of x? Remember, x follows a binomial distribution with n and p. So expectation of x is n times p. So n times p over n, that is p. So expectation of p hat is p. So what does that tell you? That tells you that p hat is an unbiased estimator for p. So this is property 1. We solved it. The second property, what is the variance of p hat? Or what is the variance of your estimator? So the variance of p hat is x over n. N is a constant. So n can be taken out, but because it's a variance, so when you take it out, you have to put a square here. So it's variance of x over n squared. Variance of x is n times p times q. So n times p times q over n squared is p times q over n. So that is a variance. And then if you take the square root of this variance, the standard error of p hat is p times q over n. Take the square root of this. Okay, so now we have what we have learned. We know that we are interested in estimating p, and we propose to use p hat, which is defined as x over n. We propose to use this to estimate p. So we know that, first of all, expectation of p hat is p. So it's unbiased. Second of all, we know that variance of p hat is p times q times over n. And that gives you standard error of p hat is the square root of this. Yes. Okay, So we know that it's unbiasedness, and we know that it's this it has this form of variance. What else do we know? Before that, actually, I want to give you an example that goes back to the previous context for the melanoma case. So in that melanoma case, our best estimate of the prevalence of the whole population in that age group in US is actually 28 over 5,000. So it's 5.6 times 10 to the minus 3. And then its standard error is square root of p times 1 minus p over 5,000. So it's 0.0011. So this is how you plug in the exact in the example. Okay. So what we have discussed here is point estimate of p. And like we talked about the population mean scenario. I told you that population sample mean is really the best estimator for population mean. And why that? It's because it's unbiased and it has the smallest variance. So in this case, can we say the same? Can we say the sample proportion is the best estimator of the population proportion? The answer is yes. And how do we prove that? The proof actually relies very critically on the relationship between binomial distribution and Bernoulli distribution. So remember, X is a binomial distribution, random variable. X follows binomial N and P. And remember what I told you, that every binomial distribution can be taken or can be viewed as a summation of Bernoulli distribution. Right? So if we write each of the xi is a Bernoulli distribution of sample size of n equals to 1 and p. So essentially, if you're looking at this 5,000 women in your sample, one after another, each one individually, it only has two possibilities when you ask the question whether or not she has melanoma. Yes and no, right? So xi can be only 1 or 0. And so it's a Bernoulli distribution with p, which is exactly the p here, which is the population prevalence. So the connection between binomial and Bernoulli distribution is the total number of success, or the total number of melanoma, or the total number of events in 5,000 sample. It really can be viewed as the sigma of each yes or no, right? So xi, it denotes the outcome of each woman. So x can be really viewed as a sigma from 1 to 5,000 of xi. So this part really is revealed for you because we talked about this connection. Every binomial random variable is a summation of Bernoulli over n, of n Bernoulli, essentially. So what does that mean in terms of p? So if x can be viewed as sigma xi, p hat is x over n. So that means if we substitute the summation part right here in the numerator, we get p hat is summation of xi over n. And what does that remind you? That essentially means that p hat is actually a mean. It's a mean estimate, because how do you estimate mean? You take summation of all the samples and then you divide it by the sample size. So p hat exactly is that formula. So although you're talking about a proportion you basically see that by the link between binomial and Bernoulli distribution, any proportion can be viewed, any p hat, the estimate of the proportion can be viewed that it is actually in the form of a mean estimate. And it is so p hat is the sample mean estimate of x1 over xn. So n is this n right here. And each one of those follow a Bernoulli distribution with p. So after we introduce until this stage, essentially understand now that p hat, although it's an estimate of population proportion, essentially, fundamentally, it's a mean estimate. It's a mean estimate of sample size n, and each sample is a Bernoulli random variable. So p hat is the estimate of p, and it's a mean estimate of that estimated from sample size n. So given this, what you learned in the previous lecture immediately can help you here, because we learned that the sample mean is always the best unbiased estimator because it has the smallest variance among all the unbiased estimators. So that answers the previous question that the sample proportion is also the best estimator of the population proportion because the sample proportion is essentially a mean estimate. Okay. So the sample proportion is a minimum variance unbiased estimate of the population proportion. That is the conclusion right here. So the next task, remember, we talk about unbiasedness, we talk about variance. The next task is really talking about interval estimate for P. And how do we achieve that? That we need to go back to that property again to use the central limit theorem. Because remember, I told you, once we establish P hat is a mean estimate, then what you have learned during the last lecture can all be a friend here. Because if P hat is a mean estimate, we already know that P hat follows a mean of P and standard error PQ over N. We already know that. We just estimate those. And then plus I tell you that P hat is a sample mean over the sample size is N. So what does that mean? That essentially means if N is large enough, it's sufficiently large enough, central limit theorem can help you to put a normal distribution here. So, let's see. Behind. Oh, yeah. So what do we have about P hat? P hat, we know that it's P and PQ over N. That is irrespective of sample size. And then if we want to further assume that N is large enough, we can put the normal distribution right here. So this is the properties with P hat. Irrespective of N, it's unbiased, it has the smallest variance. If you're willing to assume that N is large enough, then P hat is also normally distributed with this mean and this variance. So that is very similar to X bar. Remember, X bar is mu and S over sigma over square root of N. And then if you are willing to assume that N is sufficiently enough, you can put a normal distribution right here. So this is an analogy between P hat and X bar. And the fundamental connection is P hat is actually a mean estimate. Okay, so once we are clear about that, the next thing that we want to talk about is the interval estimate for P. So for that, it's actually very straightforward. Suppose we already get a point estimate of P, and now we want to estimate the confidence interval. And in the same example, how do we get that confidence interval? Use the central limit theorem here because P hat is essentially a mean estimate. So P hat can be viewed as this normal distribution with this mean and this variance. What I wrote there is the standard error. So, what is the confidence interval for P? So because we have right here, and what we do is probability of it's very similar to previously. So probability of alpha over n over this z, which is the standard normal distribution, this is a standard normal distribution, right? And we know that P hat has this normal distribution. So we can transform P hat by the standardization procedure that we learned in the first lecture. So if P hat is this normal distribution, then P hat subtract mean divided by the standard error, this whole formula, this whole number, random variable, should follow a z distribution, right? So that means you got right here, right? So because we want to estimate what is the confidence interval for P, what you need to do is to do some algebra that you move this part to each part of the boundary, and then you use P hat plus or minus right here, right? So what you get is P hat this gives you the confidence interval for P. This is essentially the same like what we did just about half an hour ago for X bar, because here, you know this is the normal distribution, so this whole part comes from the normal distribution of standardization. And then it follows a Z distribution, and then you just isolate this term by multiplying this denominator and then plus the sign from each side of the boundary, and then you get this lower boundary and this upper boundary of a confidence interval of 1 minus alpha. Okay? And remember what we have here in this formula, we have P and Q right here. So P is this P and Q is 1 minus P. We actually do not know this P. So what should we do? We actually need to substitute this by hat, P hat and Q hat. We need to substitute these two parameters by their estimate respectively. So P hat and Q hat, and this is P hat and Q hat. And you got this one. So this gives you how do you estimate the confidence interval for P. Yes? Okay. So P hat is X over N over small n. And then Q hat is 1 minus P hat. So it's 1 minus X over N. Whenever we talk about Q, it's defined as 1 minus P. So Q hat would be 1 minus P hat.
Why are you substituting the P hat and Q hat on the right side, but only the Q hat on the left side?
I wrote,
Or is that a hat?
yeah. So here actually, remember, in the population mean situation, we use S to substitute sigma, but the price that we paid is we need to use T distribution instead of normal distribution. So we need to put T here instead of Z here. Here, we actually didn't pay that price. We always put Z here. And the reason for that is here we are assuming that N is sufficiently large enough that T or Z quantile doesn't really make a difference. Because this is called the approximation confidence interval for population prevalence. Why do we call it approximation? That is a large sample size approximation. So this formula, typically, when you use this formula to estimate the interval for P, it is given that N is sufficiently large.
If n wasn't sufficiently large, would we still be using P?
No. If N is not sufficiently large, we will not discuss in this course, but if N is not sufficiently large, what we are going to use is called exact binomial distribution confidence interval. And why is that the case? Remember, P hat right here, it is X over N. And here we use a normal approximation of this mean and this variance. If I didn't tell you anything about central limit theorem, and I ask you, what is P hat? What is the distribution of this one? If you don't have the tool of normal approximation of central limit theorem, or if you know that N is not large enough to allow you to use that, the distribution of P hat or X over N is actually a derivation from binomial distribution, because you know X is binomial, right? So in other words, instead of using Z here, you can put binomial distribution here. put binomial distribution quantile, binomial distribution upper limit and lower limit, and the binomial distribution right here, and you can still do the same thing. But then the difference is you're not using Z distribution, you're not using P distribution, you're using binomial distribution. And that is called exact confidence interval for proportion, for population proportion. It's a little bit more complicated, so we're not going to touch on that. However, remember, this approximation confidence interval only works when n is sufficiently large enough.
How do you decide that the sample is large enough to choose?
Good question. I'm going to talk about that. I mean, there's no like a very clear line to say this is large and this is not large enough. The rule of thumb of, empirically, people have experienced that if, especially for p hat, it's not only about n, it's really this whole property, n times p times q. This one has to be larger than 5. So this whole product has to be larger than 5 in order for this approximation to be a good enough approximation. So essentially, you found it's not only a matter of n, it's also a matter of p and q. So, and this intuitively makes sense. If you have a very common event, so p times q is bigger because it's very common. P is close to 50%, q is close to 50%. If that is the case, n doesn't need to be that big. However, if you have a very rare event, n needs to be big to achieve this 5. So essentially, this is a recommended test or some kind of pre-screening to see whether or not you should use this central limit theorem approximation of confidence interval for population proportion. So NPQ has to be bigger than 5. But there's no a clear gray line for this magic rule about this number that you cannot use that once it's below 5. It's just the recommended rule of thumb. Yeah. So in our case, we have 5,000 is n, and then we have p. So if you multiply by this, we are higher than 5. So it's okay to use this approximation. Okay? So this slide just gives you a summarization of what is the normal approximation of confidence interval for P. It's, again, you can see that this confidence interval is centered around P hat. And then the length of this confidence interval is again decided by alpha, P, and N. So if n is bigger, confidence interval gets smaller, gets narrower. If alpha is bigger, confidence interval gets narrower. And then if p gets smaller, this confidence interval, actually it's p times q. So p times q actually is, if p gets to close to 50%, this gets bigger. So if you're estimating a more common event, a prevalence of a more common event, this confidence interval is narrower than the scenario when you are estimating a rare event. Okay, so going back to that cancer example, we got p hat equals 0.04. And the next step that we want to get is what is the 95% confidence interval for P, the population prevalence. So you can plug in those numbers. You got 0.04, which is your p hat, and then on this side, the lower side is negative 1.96, which is the z quantile value. And then you got p, which is 0.04, times 1 minus p, which is 0.96, over n, and the whole ratio, take the square root. So that would be the lower bound of the confidence interval. And then you can do the same thing by calculating the upper bound. So eventually, the confidence interval is 0.04 subtract 0.004. This is the lower bound, and the upper bound is 0.04 plus 0.004. And so the estimate of the prevalence is 0.04, so it's 4%. And then the confidence, the 95% confidence interval is 3.6% to 4.4%. Okay? So in summary, we actually finished the 2 lectures of estimation. And in those 2 estimation lectures, what we have talked about is essentially 2 questions. The first question is, what if you are given the task to estimate the population mean? And then your answer is, my best point estimate for population mean is the sample mean. And then my confidence interval estimate for population mean is a confidence interval that's centered around the sample mean estimate. And the exact formula or the format of this confidence interval, that has to take advantage of central limit theorem. Essentially, if you want to achieve a confidence interval for a population mean, you need 2 criteria. One is a sample is sufficiently large that allows you to use central limit theorem, so you could use a t distribution or a z quantile to estimate the confidence interval for the population mean. So this is one criteria. If you don't have that, what should you do? If you don't have a sufficient large enough sample, then you need the underlying distribution of your population is normal. Because if the underlying distribution of the population is normal, then you don't need central limit theorem to achieve the normal distribution of your x bar. The x bar is naturally normal, right? If you don't have that, if you don't have sample size sufficiently large enough, or if you don't have the underlying distribution is normal, then you cannot use central limit theorem. Then you cannot use what we have learned today to give a confidence interval estimate for the population mean. You can still give a point estimate, which is the sample mean, but you cannot give a confidence interval estimate. So this is the population mean. And what we learned today is population prevalence. So for population prevalence, if you're interested in estimating that, your best estimator is sample prevalence. And if you are given sufficiently large enough sample, basically if you're sampling 5,000 women, or if you're sampling enough sample to estimate the sample proportion, you can assume normal distribution by central limit theorem, and you can use the previous formula to establish the confidence interval for population prevalence. If you do not have that n assumption, if your sample size is not large enough, like n times p times q is less than 5, you can still do it, but you need the binomial exact distribution, which you haven't learned. But that's basically what we want to cover in terms of estimation. And if you take a step back, just remember, estimation, the whole task of estimation is going beyond descriptive analysis. you get a sample from a population and you're doing inference, whether it's mean or prevalence, you're really using your sample to estimate the population. So that is what we call statistical inference. And the next two lectures, what we are going to do is, okay, suppose you are interested in the population parameter. Suppose you give it an estimate, point estimate, confidence interval estimate, and then comes to your question is, suppose I have a hypothesis that my hypothesis is this population mean or this population proportion equals to a certain value that I pre-hypothesized, and then I want to do a testing to test whether the population mean is indeed my hypothesized value. If you want to perform that task, that you're talking about hypothesis testing, and we are going to spend the next two lectures about that topic. Remember, when you talk about estimation and hypothesis testing, you're always talking about population parameter, because if it's a sample estimate or if it's a sample statistic, you don't need hypothesis testing. You don't need estimation. You don't need hypothesis testing to tell you whether or not it is statistically different from your hypothesized value. You can just compare those two values, right? So remember, statistical inference, whether it's estimation or it's hypothesis testing, it's always about your population. And the fundamental thing about population is you cannot observe everything. You only observe a sample that's randomly taken from your population. That's it for today. I think we are a little bit earlier. So if you have any questions, you can ask at this moment.